Great. So yeah, thank you for the invitation. I'm excited to be here. I feel lucky that that Tina gave a great talk earlier about topological Hall-Schwarz homology, and can kind of use that as a black box here. So I'm going to talk about topological cyclic homology of elliptic cohomology, and I'll say what I mean by that in a second. And this is joint work with Christian Nazzoni, Dominic Culver, Eva Honing, and Jan Rognes. So first, I want to do a little bit of setup. So the key players are going to be these truncated Braun-Petersen spectra. And if you're not familiar with them, their coefficients are the p-local integers and then polynomial on v1 through vn. And for small n, these are other well-known spectra. So when n is -1, sort of by convention, this is HFP. And that's known to be an E-infinity ring spectrum. And when n is 0, you get the integral Einberg-MacLane spectrum, p-local integral Einberg-MacLane spectrum. That's also known to be E-infinity. And then when n is 1, you have a sum end of topological K-theory, p-local. That's also an E-infinity ring. And so sort of one of the, so there's a paper by Nazzoni and Rognes on the algebraic K-theory of topological K-theory, where they compute the algebraic K-theory mod P and V1 of the atom sum end. And so in analogy with that, we call our paper algebraic K-theory of elliptic cohomology, and we compute mod P, V1, and V2 algebraic K-theory of PP pointing bracket 2. And so that is the, so VP2 is a sum end of TMF localized at P, at least at large enough primes. And in order to make this calculation possible, so we knew that BPN was an E1 ring spectrum since like around the year 2000. But in order to make these kind of computations possible, we really needed this groundbreaking work of Han Wilson, where they prove that BPN is actually an E3 ring, and in fact, an E3 BP algebra and that's for all n. So we will use that in a key way. The other key players are the Smith-Toda complexes. So these are formed by first quotienting by the element P in degree 0 of a sphere, and then by V1 and so on through Vn. Unfortunately, they're not always known to exist. So I made a little table here of when they exist, at which primes they exist, and also at which primes they're known to be a ring spectrum, because we're also going to want our Smith-Toda complex to be a ring spectrum. And so you might think, well, like, can we push this computation that I talk about today even further and talk about like the V3 homotopy of TCB BP pointing bracket 3? But unfortunately, it's not known if there's an element V4 in the homotopy of V3, as far as I know. So so this is going to be like the limit with the current methods. So let me discuss what the result is. So this is going to be, so this is a ring, but I'm going to give a description as a polynomial on V3 module. So the answer for topological cyclic homology is that you get a isomorphism of polynomial on V3 modules on these explicit generators. So there's lambda 1, lambda 2, lambda 3, and delta. So the lambdas are in degree 2p to the I minus 1, and delta is in degree -1. And then there's this element V3 that's in 2p cubed minus 2. And then we have these other elements, which we're calling capital Xi ID, and those are in these degrees. So the key thing I want you to take away with computation is this is, it's finitely generated as a polynomial V3 module, and it's also free. So it's a free polynomial V3 module in these explicit degrees, which are in relatively low degrees. Okay, so from this, you can also compute algebraic K-theory. So this is by work of Dundas and Goodwillie and McCarthy. So there's actually also a short exact sequence. Or sorry, it's not short exact. I should say it's just an exact sequence. And really, I should put zeros here on either side. But so algebraic K-theory, mod P, V1, and V2, it only differs from TC in positive degrees by these 3 extra elements, this little FP vector space. Okay, and then we also can produce a statement about P local algebraic, or the algebraic K-theory of P local BP pointing bracket 2. So notice I sneaked in a P complete here, but actually also for the P local story, we have a statement. So mod P in V1 and V2, homotopy of K3 of BP2 agrees with the V3 inverted mod P V1 and V2 homotopy of K3 of BP pointing bracket 2. And that's with an explicit bound. So it's an isomorphism for S greater than 2p squared plus 2p minus 1. Okay, so these are some explicit computations. And I mean, I'm doing this a little bit backwards. I'm kind of telling you the computations up front, and then I will motivate them. But so let me sort of tell you why we care about the fact that this is the answer that you get. So the motivation, to motivate this, I'm going to talk about the height 0 to 1 case first. So this goes back to work of Suslin. So Suslin has this result that's mod P algebraic K theory of the algebraic closure of a field always agrees with the mod P complex K theory. So that's, of course, finally generated in free as a polynomial in V1 module. And then Bachstedt and Madsen computed the mod P topological cyclic homology of the P local integers and showed that that's finitely generated in free as a polynomial in V1 module on these explicit generators, which are actually the same generators that we saw in the other case, in the BP2 case. And so at the time, the Lichtenbaum-Quillen conjecture was not known, and they were able to verify a case of the Lichtenbaum-Quillen conjecture using this result. So the Lichtenbaum-Quillen conjecture, the way I like to phrase it is that you have sort of 2 spectral sequences. There's a motivic spectral sequence computing K theory, and then there's a kind of a tau cohomology or Galois cohomology spectral sequence computing bi-inverted K theory or some homotopy fixed points of some Galois group. And so, so here G is the Galois group of QP bar over QP. And then the key thing is that this is going to be an isomorphism in sufficiently high degrees. In fact, this is 0 connected in this case. So, so what I want you to take away from this is that the result that that this is finitely generated in free as a polynomial V1 module is sort of a shadow of Suslin rigidity. And then from height 1 to height 2, there's results of Oswami and Rognes from 2002. So they computed mod P and V1 homotopy of K theory of BP pointing bracket 1. Again, it's finitely generated in free as a polynomial in V2 module on these explicit generators. Again, these are the same generators we're seeing, except we see a few extra. And here, this is a bit, there's some speculative stuff here, but in 2014, John Rognes suggests that there may be some analogous story where you replace QP by a fraction field of the P complete Vn inverted BP pointing bracket 1. So if you take BP pointing bracket 1, you P complete, and then invert V1, that's LP. So G is some sort of speculative Galois group of omega 1 over fraction field of LP, and this is some maximal extension. I mean, and this doesn't completely come out of nowhere. This is based on some computations with Cristiano Aussoni, where they, so we don't actually know what the spectrum of the fraction field of LP is, but we sort of know what its K theory is by looking at localization sequences. So, but again, the key takeaway I want you to have from this is that the fact that this is a finitely generated and free polynomial in V2 module is some shadow of a higher height analog of Suslin rigidity, conjecturally. And similarly, you have a similar story for BP pointing bracket 2. Okay. So there's also the story of Redshift, which is also sort of coming from it's rooted in these Lichtenbaum-Quilling conjectures at height 1. And I want to phrase sort of two versions of the Redshift conjecture and say how they fit into this story. So for the Redshift conjecture, you always need some notion of chromatic height. So the notions we will use today are the following. So let's say that X is bounded below NP complete. Then we say that X has pure FP type N if after smashing with some finite complex of type N, that's a finite cell S module such that the nth Morava K theory is non-trivial, but the n minus first Morava K theory is trivial. And so there's a nice theory of these developed by Hopkins, Donuts, Hopkins, and Smith, which says that these always have a Vn to some power self-map. So in particular, these are polynomial on Vn module, these homotopy groups. And so you can always ask, is this a finitely generated and free polynomial on Vn? And here I'm going to put to the D just to be safe module. And then, so then a conjecture of John Rogness from the year 2000 and Norbert Wolfach in 2000, phrased as the chromatic redshift problem, is what I'm calling the pure FP type redshift conjecture. So this is a strong form of the redshift conjecture. And I'm adding the qualifier regular here, just again, to be safe. But so suppose R is a regular E1 ring with pure FP type N, then TC of R has pure FP type N plus 1. So the general philosophy of the redshift conjecture is that when you apply either algebraic K theory or topological cyclic homology, you're increasing the chromatic height by 1. And this is one way to precisely formulate it. So if R has pure FP type N, then TC of R has pure FP type N plus 1. And so in this very strong form, some of the only known examples we have are the following. So there's the Bokstad-Madsen result at the P local integers. And then there's several other results at height 0 that I won't mention at the moment. But then at height 1, there's results of Aussoni and Rogness for the atom summand, topological K theory by Aussoni, and then connective Morava K1 by Aussoni and Rogness. And then our result is really the first evidence for this particular conjecture at heights greater than going from heights 2 to 3 or higher. And now I know many of you in the audience are familiar with the rest of the Han-Wilson results paper, so I want to say a little bit about that as well. So, so there's another formulation of the redshift conjecture, which is the following. So we say that X has X has telescopic complexity n. So remember, we had some Vn to some power self map of Vn of f of n minus 1. You could take the colimit of iterates of that self map, and that's going to form this telescope, the Vn inverted f of n minus 1. And so you can ask whether the map from f of n minus 1 smash x to the telescope is whether this map induces an isomorphism in homotopy for s sufficiently large. So this is so I just want to make a remark that the pure FP type redshift conjecture, this implies the following, which is a slightly weaker formulation. So this is not exactly how it's phrased also in Guido's book of conjectures and by Alsania Rognes in 2008, but it's very closely related. So if R is a, let's say again, regular E1 ring with telescopic complexity n, then the algebraic K-theory of R has telescopic complexity n plus 1. So in the same, very impressive paper where they show that BPN has the 3-ring spectrum, they also prove this form of the redshift conjecture for all P and all N. So they also prove the telescopic complexity redshift conjecture for all P and N. And so so our result also gives an independent proof of this conjecture in the case P equals 2 and N greater or equal to 5, because we just use the theorem A from Wilson that BPN is an E3 ring in our computations. So I just wanted to kind of highlight that there are sort of different notions of redshift conjectures and how these are sort of related. Are there any questions at this point? I think that would be a good point. See, there was something in the chat. Oh, wait, that was from earlier, maybe. Oh no, that was okay, maybe a typo. Sorry about that. Okay. So right. So then the next part of the talk is going to be a sketch of the proof. So basically what I'm going to do is at the same time sketch how we compute topological cyclic homology and also outline how one computes topological cyclic homology in general. So many of the things I described will work more generally, but then I will sort of be working in this special case for BP pointy bracket 2. So the first step is always to compute topological Hausdorff homology, which we had a really nice introduction to in the previous talk. And so topological Hausdorff homology has this extra structure. It has also an S1 action, and it has the cyclotomic structure map. And so these will be very important players. So first of all, though, topological Hausdorff homology, well, after smashing with a finite complex, it's often much simpler. So actually, this THH of BP pointy bracket 2 mod P and V1 and V2, excuse me, this is actually an HFP algebra. So HFP algebras are relatively easy to understand. Basically, you need to compute the homology of it and then understand the subalgebra of comodal primitives. So you do that, and what you get is you get an exterior algebra on lambda 1, lambda 2, lambda 3, tensored with a polynomial algebra on a class mu. And so these lambdas are the same lambdas that showed up in the computation, and mu is also secretly there, and I will say more about that later. So the degree of lambda I is 2p to the I minus 1, the degree of mu is 2p cubed. Okay. So then the next step is to prove what is a bit of abusive terminology to call it the Siegel conjecture, but let's call it that for now. So that the question of whether this map from phi p, which is the tape value Frobenius map from the V2 homotopy of THH to the V2 homotopy of THH of BP pointing bracket 2, the CP construction, we want to show that that is sufficiently co-connective. So this is actually the geometric fixed points, the CP geometric fixed points of THH. And this map is the right-hand map in the isotropy separation diagram, if you're familiar with that. Okay, so this actually, what we prove is that this can be identified with the localization map, the map from the map given here from exterior and lambda 1, lambda 2, lambda 3, tensor polynomial and mu, and then just inverting mu. Although this mu is secretly coming from this generator T in the spectral sequence. So I'm going to gloss over that for now. In particular, this map is an isomorphism for a star greater than 2p squared plus 2p minus 3. So that gives us an explicit sort of lower bound. Okay. Right, so my plan is to talk about this step 2 in a bit more detail at the end, as long as there is time. But then once you have step 2, what you do is you bootstrap up from THH and the CPT construction up to topological negative cyclic homology and TP. So I think I had a definition of this before, but maybe let me just include this again. So TC minus with this notation that T is THH, that's T upper HS1, and TP is topological Hauschel homology, and then the S1 Tate construction. So here I'm also going to write V for V of 2 from now on, just to simplify the notation. So, I claim we also know that this map and this map is 2p squared plus 2p minus 3 co-connected. And that follows from step 2, together with Solidus's theorem, or really a version that's due to Blockstedt, Brunner, Rognus, and Luno Nielsen. So this is also Solidus's theorem. So that tells you that, so in the case n equals, let's see, okay, I have a typo here, sorry. So it should be n minus 1. So in the case n equals 1, this is just mod p v1 v2 homotopy of topological Hauschel homology of BP2 mapping to the CP Tate construction. So then this is exactly the map we had before, which I called var p. So this is just different notation. So var p is gamma 1 hat. And so once you know this is sufficiently co-connected for n equals 1, then Solidus's theorem says it's also true for all the higher n's. And then because this is a pullback, it's also true for this map. Okay, so then you use that to kind of bootstrap your way up to the top here. So each of these maps on the left and the maps on the right are 2p squared plus 2p minus 3 co-connected because they're exactly these maps. So first you compute both of these things downstairs. Then you use this CP Tate spectral sequence to understand the homotopy CP fixed spectrum, homotopy CP fixed point spectral sequence. And then you know this is sufficiently co-connected. So you can use that to infer things about this, and so on and so on and so on. So this is a vast oversimplification of what we do, but it sort of gets at the idea of how you go from this information to understanding TC minus and TP. Okay. And then the next step is to compute the following homotopy equalizer. So this is, here we're really using Nicolaus and Schulze from the year 2018. And I'll say a little bit about how that compares to how one would do this before 2018 in a second. So first of all, Nicolaus and Schulze showed that TC, which I really actually haven't defined yet, but I'm going to say that in black box that's for now. But this is actually equivalent to this homotopy equalizer for at least for bounded below, for bounded below spectra, or I should say when THH of your ring spectrum is bounded below. So in particular for BP pointing bracket 2, because BP pointing bracket 2 is connective. I'm also suppressing some P completions here, but so we want to compute these two maps, and then that allows us to compute TC. And what happens here is that we have a canonical map, and then there's sort of an isomorphism that we call G. And in the previously known cases, this was sort of computed to be an isomorphism directly. And now we know that this is an isomorphism as a consequence of the Tate orbit lemma by Nicolaus and Schulze. But I just want to point out that this is an interesting isomorphism. And in some sense, the canonical map and this var phi map are not that hard to understand, because at least in our computations, we see that this is just the mu inverted topological negative cyclic homology. And this is just the T inverted topological negative cyclic homology. So in one sense, going one way, you just localize it T, the other way you localize it mu. Hopefully I said that right. That concerned here. Yeah, so then, but then this isomorphism carries a lot of information. And to compute the equalizer, you either have to go around this way and compute this equalizer, or you have to go around this way and compute the equalizer with that map. So let me just say a little bit about how this relates to how one would have done this before Nicolaus and Schulze. So basically, before Nicolaus and Schulze, we would have computed TC in basically the same way, but we would have only known that it gave the correct answer above the bound given by the Siegel conjecture. And this isn't precisely why it's the case, but let me just sort of indicate that. So we have this restriction map going from TF to TF, and then we have a canonical map going from TC minus to TP. And this sits in a commutative diagram, which is just the isotropy separation diagram. You just take the isotropy separation diagram for each CP to the n and take the limit. And by Salidas' theorem and the calculation of the Siegel conjecture calculation, we know that each of these maps are 2p squared plus 2p minus 3 connected or co-connected. So that says that we can actually compute everything down here, and that tells us how to compute the top part. And then, so TC, I think maybe that's a problem. So TC is of BP2 is the equalizer. So that's defined to be the homotopy equalizer of 1 and R on TF. Yeah, sorry, I guess I decided my target audience was people who have seen that before. Sorry about that. Okay. So yeah, so this is TC. That's this homotopy equalizer. And so to compute TC, you would want to compute this R map and then take the equalizer with the homotopy equalizer with this just the identity. And so what you would do is you would compute this canonical map in sufficiently high degrees. So that would give you a kind of lower, like that would give you the computation above some degree. And then you also knew the computation below some degree. So this comes from a theorem of Waldhausen and the Dundas-Cooley-McCarthy theorem. So we also know that this map is 2p squared minus 1 connected. But the problem using the traditional approach is that this leaves a gap from 2p squared minus 1 to 2p squared plus 2p minus 3. Whereas in the case of BP0 and BP1, there was no gap, just for kind of degree reasons. So we really do use the Nicolau-Schulze approach, and this is important for us mainly to compute this gap of degrees here. Okay, so that was sort of a side comment. And then step 4 continued. I just wanted to sketch a little bit what the answer looks like, although I'm not going to tell you all of the things that go into it. So this TC minus splits into 3 different pieces, at least in positive degrees. There's a piece I'm calling A, B, and C. Here, let me just do that. Okay. So the A part is exterior on lambda 1, lambda 2, lambda 3, tensor polynomial on T mu, and T mu is going to correspond to B3. And the B part, I'm not going to say exactly what it is, but it's some infinite product of V3 torsion modules. And then the C part, I claim we don't actually have to understand too well, at least for the purposes of the talk. So this doesn't contribute to TC. So then to compute the homotopy equalizer, you want to compute the equalizer and co-equalizer of the maps from TC minus to TP. One of the maps is the identity. So on the A part, both maps turn out to be basically the identity. So you get a copy of A here and a copy of A. The B part is where a lot of the interesting stuff goes on. So there, you get some equalizer, and basically what happens is that you have an infinite product of V3 torsion modules, and this is also an infinite product of V3 torsion modules. And the way I think about it is it's like you have a sequential limit of polynomial V3 torsion modules where the torsion is getting higher and higher. So in the limit, you would get like maybe a power series on polynomial V3, but it's no different from a polynomial algebra and polynomial in V3 in each homogeneous degree. So yeah, you have the sequential limit of increasing V3 torsion, and then you rewrite that sequential limit as like an equalizer between 2 products. And that's what's essentially what's going on here. So this ends up being also V3 torsion free. And because that sequence was Mittag-Leffler, the co-kernel is 0. And then here we have 0 and the identity. So there's no equalizer or co-equalizer. So that's just a sketch of like what the different pieces are from the calculation of TC. Okay. And how are we doing on time? Should I be ending soon?
You have 10 minutes left.
Oh, perfect, perfect. Okay, so then I have time to sketch step 2, which is, yeah, I think it's a, particularly interesting part of the proof because it sort of introduces these power operations that you could also apply in other contexts, I think. So that's why I wanted to talk about that. So first, I want to do a proof sketch of step 2. And first, I'm just going to make some claims about how things go. So the idea is you take these elements alpha 1, beta 1 prime, which is like a box sign on beta 1, and gamma 1 prime prime, also like a mod p and v1 box sign on gamma 1 and v2. And so I claim that we can prove that these actually map non-trivially to here. And so to prove that, it takes some work, and that was what I was going to talk about next. But let me say how, if you can show that, you can compute the CP take construction. So basically, you take these classes and you detect them here. So since they're also then in TC, that means they're in the kernel of 1 minus, sorry, I didn't have TC in the picture here. Maybe I wanted to just write TC there. Okay, so since these are also TC classes, and that means they're in the equalizer of 1 and R, and in other words, the kernel of R. So that means that's they map to 0 here, basically. So particularly, they also map to 0 in the take construction, and that means that they're elements that are in sort of both of the spectral sequences here. So you have the left-hand side is producing the spectral sequence whose abutment is this, and then the whole upper half plane is a spectral sequence computing this. So these are all classes that survive in here, but you can prove they don't survive in here. And this forces certain differentials, which also happen to come from the 0 line. So you can prove that you have these different differentials. And then these actually generate all the differentials. In this CP Tate spectral sequence. So by detecting these classes, you can generate all the differentials here. And then using that bootstrapping procedure, you can produce the rest of the differentials in the CP to the n homotopy fixed point in Tate spectral sequences. So this is one of the kind of key starting points. So then the question is, how do you actually show that these elements map non-trivially here? And really what we will do is we'll show that they map, so let me say something about that. So we want to prove that alpha 1, beta 1 prime, gamma 1 prime prime, and v2 map to these classes. And the story will be a little bit different.
Gabe, it's really v3, not v2. So.
Oh, thank you.
Yeah.
Yep. Sorry about that. Did I write that anywhere else? Hopefully not. Oh, yes, I did here. Yeah, thanks. Okay. All right, so we want to prove that each of these classes map to these classes. And so the key thing is to construct certain homotopy power operations. And just for the purposes of this talk, I'm going to write them like this. So this upper K is actually the index. So let me try and make that smaller. So these are homotopy power operations, but notice that they sort of shift from like a type n complex to a type n+1 complex. And these are homotopy power operations that you have for E2 rings. So in the paper by Alsoni and Rognes from 2002 on algebraic K-theory of topological K-theory, they compute similar power operations to these for E infinity rings. So so why E2 here? Well, when you take topological Haschel tomology of BP2, which is an E3 ring, you decrease the n by 1. So topological Haschel tomology of BP2 is an E2 ring. This is by like, I think of it as Deligne's conjecture, even though Deligne's conjecture was about topological Haschel cohomology. Okay, so all right, so yeah, each of these are E2 rings. And so we can apply these power operations to them. And then there's a bit of a subtlety here. So we also can prove a Cartan formula, but this is really in the presence of a little bit extra structure. So the Cartan formula that we prove, we actually do this in the mod PV1 homotopy of TC of BP itself. So we use actually that BP2 as a BP algebra, a structured BP algebra. And then we also use these computations of Jean Rognes from 2020. And we extend those just in like by a few differentials in the mod P and like after smashing with some Smith-Toda complex. So you have some Cartan formula so that you go from T to lambda 1 to T to the P times this power operation on lambda 1. And then you can just, let's say we define lambda 2 to be the power operation on this lambda 1, and then you have to check that that way of defining lambda 2 is consistent with the other kind of way of defining lambda 2 as an element in THH. And then similarly here, and then we have this power operation takes you to lambda 3. And then also we have these kind of power operations that take you from alpha 1 to beta 1 prime, and then from beta 1 prime to gamma 1 prime prime. And again, I'm sweeping some things under the rug. So, but at least in V2 homotopy, this is exactly what happens. Okay, so you can use these. So then you basically use these power operations. And then there's sort of one other ingredient here, which is that you use these nth order approximate homotopy fixed point spectral sequences, which, so basically what you do is you take the homotopy fixed points and you filter it by skeleton, which is the same way you would build the homotopy fixed point spectral sequence. And then you just truncate that filtration at some stage. And so the key thing is that then you kind of lose a lot of things in, I don't know, high or low filtration that would kind of distract you from the fact that these elements are all detected. So, and then the argument's a bit different for the different cases, but combining these two approaches, you show that then alpha 1 maps to T lambda 1, beta 1 prime maps to T to the P lambda 2, and gamma 1 prime maps to T to the P squared lambda 3, and V3 maps to T. Okay. So that was the end of my sketch of step 2 in more detail. And I think I will actually end my talk there. So feel free to ask questions. And thanks for listening.